All right, next up, we got chapter 5. So obviously there's a lot of stuff. We're not going to cover it all in depth. We're just going to kind of go through the basics. So what is energy? Energy is defined as the capacity to do work, right? If you got a lot of energy, you can do a lot of work. If you don't have a lot of energy, you can't do a lot of work. Potential versus kinetic energy. Potential energy would be defined as kind of stored energy, and then kinetic energy is energy due to motion. Right, next up, we're talking about thermal energy, kinetic energy, temperature relationship. Basically, the faster a molecule is vibrating or moving, the more thermal energy it has, and the higher the temperature, right? So faster vibration goes to higher temperature. And so in chemistry, right, most of the time we're not actually talking about doing work, we're talking about heat. Heat is the movement of thermal energy, right? So things will transfer heat to one another, their molecules will vibrate and slam into each other, and they'll get to the point where they have the same temperature. Thermal equilibrium is reached at the end. Endo versus exothermic. Exo is releasing heat, right? So whatever you're talking about is releasing heat. So burning is the most common example of an exothermic reactions. Endo, whatever you're talking about, is absorbing heat. So something like boiling water. The water is absorbing the heat, and so it's undergoing an endothermic reaction. Units of heat, just joules and calorie. Kind of know what they are. You don't have to interconvert between the two. Just know that they're units of energy. We also use kilojoules, which means 1,000 regular joules. Specific heat of capacity, really the main one we talk about is specific heat capacity, and that's how much heat or how much energy is required to raise 1 gram of a substance by 1 degree Celsius. The regular heat capacity is just how much temperature ranges up to increase the substance of a temperature by 1 degree Celsius. Doesn't have this gram specification. And then the molar, instead of 1 gram, it's 1 mole. And you actually don't have to memorize specific heat of water. I'll give you that on the test. So most of these problems are Q equals MCAT type of problems. And so Q equals MC delta T. Q is obviously heat. M is obviously mass. C here is specific heat. Should actually be a capital C. And then delta T is equal to the change in temperature, and so it's the final temperature minus the initial temperature. So that's one of the things about the problems. The other things about the problems is that they generally start off with this negative Q of the system equals Q of the surroundings, or vice versa. It doesn't matter where you put the negative sign as long as it's only on one of them. And so what this means is that all the heat gained or lost by the system is gained or lost by the surroundings, right? We can't create energy, we can't destroy energy. So all we can do is transfer it from one place to another. So we won't do any actual problem work here. You're gonna just have to take a look at your notes for that kind of stuff. But a lot of problems are gonna be something like this. So be able to calculate Q through kind of a plug and chug method, and then be able to use this negative Q of the system is equal Q of the surroundings type of thing as well. All right. State function, that's just something that doesn't matter how you got there. It's just the beginning and the end. So altitude is a state function. It doesn't matter if you went up 5 miles, went down 5 miles, went up 5 miles again. All that matters is your start and end point, which is delta H. Enthalpy is a state function, right? So delta H, enthalpy is just delta H, and for our classes, or for our purposes, delta H is essentially just equal to heat. So it's just the heat of something. So for exothermic, the system, since it's losing heat, it would have a negative delta H, and then endothermic, since it's absorbing, it would have a positive delta H. Right. So be able to do that kinds of stuff. Calculating heats of reaction, standard enthalpies from, or standard reaction enthalpies from standard enthalpies, and Hess's law. You can take a look in all the notes for that kind of stuff. Let's just go over it super quickly though. So let's take a look at an example of a heat of a reaction. So this would be something like maybe you have this equation. C3H8 plus 5O2 goes to 3CO2 plus 4H2O. And then you can have a delta H here of negative 2044 kilojoules. So a couple things. What does this negative tells you? This negative tells you this reaction is exothermic. If you actually look at the reaction, it's a combustion reaction, so that makes sense. And then this value, although it just has units of kilojoules, the way you can think of these units are kilojoules per mole of reaction, per mole of reaction. So for example, if you burn 1 mole of C3H8, right, since there's a 1 here, you just get negative 244 kilojoules from the system, right? So the system loses energy, the surroundings gain energy. But for example, if you burn 2 moles of C3H8, then you get twice as many, so you negative 4088 kilojoules, right? So it's just the relationship. So these are essentially kind of like a mole to mole type of conversion, but it's an energy to mole conversion. What you want to look for is the coefficient of whatever you're interested in and the energy. And again, you don't have to be asked for one thing, you can be asked for any of them, but you just have to take a look at the coefficients, right? So to get this much energy out, you need to burn 1 mole of C3H8, 5 moles of O2, and you'll produce 3 moles of CO2 and 4 moles of H2O. All right, next up, we've got this reaction enthalpy for standard enthalpies. And so this stuff's pretty simple overall. That's when you're given kind of data about these delta H of formations. Again, this F stands for formation, and asked to solve for the delta H of the reaction here. So what is this value? And basically what you need to know is you need to sum all of these delta H's. So sum all of them. But before we can do that, we got to figure out what their values are. So CH4, if we look over here, CH4 is negative 75. But this is delta H of formation. So formation. In chemistry, we destroy reactants and create products. So since we're not forming it, this value is actually opposite of what it is. And so to this side, we're going to multiply by a negative number times a negative number to flip the sign here and make this positive. That way we know we're destroying it, not forming it, right? So this is negative, so when you make it positive, that means it takes energy to break apart CH4. And so the other thing we have to pay attention to is the coefficient. Right here, the coefficient is just 1, so we're not changing how many. This is per mole, this is 1 mole, so we're good there. So we can just write essentially -1 times -75. And then we add our next component to it. Again, we multiply by a negative because we're not forming it, we're destroying it. In this case, a -3 because we have 3 of them. But you see Cl2 is not listed here, and that's something that you just kind of got to memorize. The delta H of formation in anything in its elemental or diatomic form is 0. So this just automatically goes to 0. Next up, we got CHCl3. So this time we're not going to multiply by negative because we are forming it. It is a product. So you just pull this number from here. And then this time, in this case, we're just going to multiply by 1 because we only have 1 mole of it. So this gets plus a -134. And then finally here, again, no multiplying by negative because it's a product. Here we have 3 of them. So we're going to multiply times 3. And so this ends up being plus 3 times -92. And then if you go ahead and plug and chug through the math, what you end up getting is -335 kilojoules, which is then the answer. So overall, pretty simple to do. Reactants, flip the sign because you're destroying them, not forming them. Products, keep the sign the same. And then just pay attention to your coefficients, right? Coefficients will tell you what number to multiply it by. So overall, it should be pretty straightforward. All right, last up, we got Hess's law. So let's take a look at an example of this type of problem. So this is the kind of example where you want a delta H of some kind of reaction, but you don't know it, but you're given some other information. And so you have to decide whether you're going to flip these reactions, multiply them, add them, do whatever you need to do to figure out what your equation is over here. So the thing you want to do is you want to take a look at what you want to figure out. So in this equation of our unknown, we have two NOs on the reactant sides. So we have to take a look at where else NO is. And if you look at these two other equations, the only place NOs is located is over here. So if it's only located here, it had to have come from here in order to get for our givens to our unknowns. And so we see that it's on the wrong side. It's a reactant here in the top equation, and then it's a product down here in the bottom equation. And so in order to flip a reaction, what we do is we multiply by a negative number. When you multiply by a negative number, you're multiplying this delta H by that negative number, and you're flipping the reaction over. So since we have our coefficients are the same, right, 2 and 2, we're just going to multiply by -1 because we just want to flip the reaction. We don't want to do anything else other than just flip the reaction. Next up, we look at our next component, our O2. So we want to think about where's this O2 coming from. And if we see O2, it comes from here and from here. So in this case, we don't know where it comes from. When we don't know where it comes from, the best thing to kind of do is to just ignore it for now. We'll come back to it, but for now, we're just going to ignore it. Finally, we have this 2NO2. If you take a look at the equations, there's only one place where NO2 is found, and it's over here. And it's a product up here, it's a product down here, so we don't have to do anything in terms of flipping the sign. So we're going to multiply by a positive number. But we do want to make this 1 down here into this 2 up here. So to do that, we multiply the equation by 2. And so let's see what happens when we do that to these things. So this guy right here, I'm going to flip it. So I'll go 2NO goes to N2 plus O2. And then this equation down here, I'm going to keep it the same. I'm going to double it. So it's N2 plus O2 plus 2O2 goes to 2NO2, right? So I doubled it. The next thing I'm going to want to try to do to get where I'm going is to sum these two. So let's go ahead and sum them. And things that show up on both sides will cancel out. So this one of these oxygens will cancel out with this oxygen. And this N2 will completely cancel out with this N2. So what we end up is with 2NO plus an O2 going to 2NO2. And so if we take a look at what we wanted, we have that component, we have this component, we have that component. Our equation looks just like what we want it to look like. And so the same things we did to the equations, we have to do to the numbers, right? So you have to go out and carry out these functions. Multiply 183 by -1, and then multiply 33 by 2. And then just like the equations, we sum the equations. So we're going to sum these two up. And you should get -117 kilojoules. All these units were in kilojoules, my bad. Yeah, that's basically how you do this problem. If you want to flip a reaction, multiply by -1. You want to double, triple it, multiply by 2, 3. And then sum equations up to try to get to where you want to go. We saw some examples in class. There's plenty of examples in your homework, so it shouldn't be too bad.